Yeah, welcome everyone. My name is Alejandro, and I'm a research engineer here at Cohere Labs. And I'm here today with some of the core members of TinyAya. And Diana, Julia, Daniel, and I are going to be presenting and sharing all the work we've been doing with TinyAya. Um, so, yeah, we're going to walk through all the different details and stages of this model. Just some introduction, TinyAya is a family of small open-weight multilingual models that we recently released. And yeah, this is a deep dive. So we're going to cover the full pipeline, pre-training, post-training, evaluation, on-device deployment, all the details. And the goal is to give you not just what we build, but also why we decided to build it in this way. So we will go through the different choices that we made throughout the process. During the presentation, I guess you can ask some questions on the chat, but we will also leave some time at the end for questions. So you'll have an opportunity to ask all your questions. And yeah, we also released a technical report, includes a lot of details. If you read it, that's perfect. If you didn't have a chance, also take a look, and we cover there some of the details more in depth. All right, so let's get started. Um, TinyAya, we're trying to solve a problem that we believe is very important, and is that multilingual AI progress has been uneven. And we believe that's a representation problem. We believe that all languages deserve to be represented in AI models because many people interact with these models, and we want people to be able to do it in their native languages. And many of the models that are released nowadays are really good in a few languages and not that good in languages that do not have as many speakers as, let's say, English or Spanish or French. So we can take a look at this chart, and we can see that performance drops quite fast, quite sharply, as you move from the most resource languages like European languages to all the way to African languages, where performance decreases quite fast. And that gaps means that entire communities are being left out of the AI revolution. And we believe this problem can be solved, and we try to do some of that with TinyAya. Um, so basically, we asked like the question of, can we build a small model? So something that is efficient and can run offline, maybe in your phone, in your browser, and that can serve as many people as possible in their native languages. So this is something we're gonna repeat quite a lot during the presentation. And yeah, I think it's the main idea that we want you to take away from the presentation, and is that balanced multilingual performance can be and should be a priority, and achieving it is a design problem. So all the decisions matter, from the tokenizer, the data that we use, the training recipe, post-training strategy. When you are intentional about all these different stages and choices, you can build a model that is truly multilingual. And this is the mindset that we had from day one. Um, yeah, so what did we release? We released quite a lot of things. Five different models, all 3.3 billion parameters, one base model, and four SFT models, so instruction models, one that covers all the languages, is the global model, and then three regional models. And those are available on Hugging Face and in Kaggle. TinyAya supports more than 70 languages, and we have, as I mentioned before, the tech report, we have a demo, and you can use it on your phone using the PocketPal app. And this is the agenda for today. So we're going to be talking about pre-training, post-training, evaluation, on-device deployment, and we will finish with some conclusions and still open questions. And with that, I will pass it to Diana that we will be talking about pre-training.
Hi everyone. I'm Diana. I was a research scholar in 2025, and this is the outcome of my research scholar project. So I'm going to be going over the pre-training portion for the tiny IM models. First, we're going to start with the tokenizer, and this was an area where there was a significant amount of design that we had to do because we planned on releasing a model family, right? Where each model covers a different set of languages. So the question is, do you have one tokenizer per model, or do you have a shared tokenizer for all of the models, right? Um, you always have this trade-off where the more languages that you have in the tokenizer, the worse the representation. And in general, this is not a problem just in our model family, but across multilingual models. The way that they're trained is that they just sample from the training distribution. So low resource languages that are less represented in the training data will be worse represented in the tokenizer, which means stuff like compression ratio is going to be worse. Text in lower resource languages will be more fragmented. And this leads to other complications. So you have more tokens per sequence per word. So there's slower inference, worse learning signal, and wasted capacity. There's a variety of work on this subject, but we wanted to tackle this problem in our model design and really intentionally prioritize multilingual support in our tokenizer. So yes, we decided to share one tokenizer across all 5 models, which simplifies a lot of things downstream, like post-training and merging. Um, we made sure to use a large vocabulary size so that all of the languages can be well represented within the vocabulary. But the key thing is that we trained the tokenizer uses using a weighted sampling across languages where you prioritize both the data distribution, which, you just sort of have to do if you want efficient training, but also within language family and script buckets, making sure that there's sufficient representation for each family and script. Um, because that grouping sort of optimizes for shared tokens, but you still want to make sure that script that has only one language that uses it um, would still have a good representation. So at the same time, that prevents high resource languages from dominating the tokenizer training. So if you want to know more about that design, we have a paper on this topic called One Tokenizer to Rule Them All. It was released last year. Um, so we used those findings and we trained on 50 gigabytes of data sampled from FineWeb 2, and we used the GPT-4o regex for pre-tokenization, which is pretty standard, but no normalization. And you can see here we have tokenizer efficiency by script, comparing the green TinyIA model and some of our competitors like Quen and Gemma. And you can see that for the majority of the scripts here, TinyAI is actually the most efficient where there are the least amount of average tokens per character. So we're winning in scripts like Javanese, Cyrillic, um, Lao, while still maintaining a good performance on Latin script, which is of course the majority of our data and the majority of the European languages. Okay, moving on to our pre-training data, we used a large variety of sources. In particular, we had a large corpus of public common crawl data, and this was further filtered down. We also used proprietary data, and in total, this covered 70 languages and programming languages as well. Code was included because it's been found that code improves the performance of um, language, but also reasoning and NLU. There's a paper from Cohere Labs about that as well. So to create the mix, we balanced across the different languages in a similar manner as we discussed with the tokenizer. So we're upweighting lower resource languages while still trying to ensure good performance and competitive performance on higher resource languages. Um, then for the filtering pipeline, we have language ID and stop word filtering. So this helps direct the data into different language buckets, right? Then there's heuristic cleaning from raw sources, deduplication, and domain classifying, so that we can make sure that domains such as STEM are higher weighted because those are found to be more informative, and quality filtering. Of course, we want more high quality data. We also have a cooldown phase. So the data that I was discussed is used in the majority of the pre-training. In the cooldown, we also upsample the highest quality data sets and add more instruction style data. Um, yeah, so that we're well set up for post-training. Now into the architecture, we use pretty much the same architecture as Command A. So if you want to learn more, you can read this paper. Um, but the sort of key details are that we use parallel transformer blocks, which is really good for efficiency because you don't have to calculate it sequentially, and it doesn't impact model quality at all. So in general, you'll find that a lot of our decisions are intended to optimize training efficiency. Um, we also used interleaved. Oh, I'm so sorry. Speed run through the other ones, but please read the report for more. Interleaved attention, which alternates using rope and nope. So you have the full attention window in order to, have a large context, and then you also have some layers with sliding window attention, which is much more efficient to compute. Swigglue, yes, better training stability, better downstream performance. This is our activation function, and grouped query attention. So the key value heads share across 16 queue heads. So this reduces the inference memory footprint, and that enables us for good on-device deployment, which we'll be discussing later on in the slides. Just wanted to do a quick mention also, our architecture was replicated by Sebastian Roschka, so please check out his blog also for additional information. Yes, and now, okay, more detail on the training itself. The pre-training was done on 6 trillion tokens. This is across 256 H100 GPUs. We used a warm-up stable decay learning rate, which has become fairly standard for large-scale training runs like this because you don't have to decide on the token budget ahead of time. With a cosine learning rate, you are not able to shift the cosine curve after the fact, right? But warm-up stable decay, basically you have a linear warm-up and then you have a flat, constant learning rate during the main phase of training. So you can extend that very easily. And then decay brings the learning rate to a value close to zero. And we chose the hyperparameters using smaller scale ablations, where we did 200 billion token training runs to compare different data mix ablations and hyperparameter choices. So we found that doing this smaller scale training runs provided findings that are pretty representative of the full scale performance. And we also did the same thing on cooldown. We also did mixed precision training, which again, the motivation is more efficient training. So whatever pieces of information you're able to store in lower precision, we do so. We keep the main weights and optimizer states in floating point 32. Model weights are cast to BF16 once we're doing the computation. And sensitive operations like softmax, layer norm, output embeddings are in floating point 32, because the more information, the better. And attention is in BF16. Um, Later, after training, we cast to BF16. And all of this is being done on FACS, which is based on Jack's distributing training framework. Yeah, so in summary, that was a lot of information, but takeaways are we're using a single tokenizer with balanced representation of all of our languages. Training is done on 6 trillion tokens from 70 languages and code. Lower resource languages are upweighted. We use a dense 335 billion parameter architecture. Floating point 8 mixed precision training on 256 GPUs using the warm-up stable decay learning rate schedule. And we did ablations on 200 billion tokens with 40 billion tokens for cooldown to make decisions on the full-scale training. Thank you. Now I'm passing off to Daniel.
Yep. Hi, everyone. My name is Daniel, and I co-led the post training. So happy to talk more about it. Do I have control of the slides, Alejandro? I do, right?
I don't know. Just I'll try to pass the slide, otherwise just say
I'll say
next slide.
next. All right. Yeah. Okay, so for post-training, the most important thing is high quality instruction data, right? And this is usually available in plenty if you're just doing a English model. But since we're tackling 70 languages, this gets tricky. And what happens usually is when you're also dealing with low resource languages, this gets even tougher. So the solution here is essentially synthetic data, right? And there are very lazy ways to do this. You could just take all of your data, translate it, and then you're done. But that doesn't solve anything. So our solution is to actually collect high quality internal, external data sets and then extend coverage via a multi-stage synthetic data pipeline. And a lot of thought has gone into the design of this, which I will talk about next. Okay, so four things that we absolutely wanted to do when we were designing this pipeline is first thing is it has to be language specific. Every language is different in the kind of treatment it requires, in the kind of care it requires, and what kind of operations you want to do. It has to be dataset specific as well because some datasets require just translations, some require better completions, some require better prompts, right? Or improved prompts. So we want to have that kind of flexibility as well. We also want it to be reproducible because whenever we're doing experiments or you're selecting a random subset, we want that to be reproducible because we want to do good science. And the fourth one, and perhaps the most important one, is we want it to be built on open research. Our team cares a lot about this field. We've published a bunch of work, and we want to show how fitting all these pieces together actually gets us to our goal. Next. So this is what our synthetic data pipeline looks like. And I will go over it in brief, and then we can go over each of these pieces. So essentially what happens is you collect a bunch of source data sets. You have a translation phase. After this, if your translation of the data sets is of a high enough quality, you can then directly pass it to your final mix. But if it's not of high enough quality, which is most of the time the cases, that's when it gets interesting, right? So here, what you're going to do is you translate the prompts, and then you can kind of improve the prompts. After that, you will get better completions for each of them. And then you add it to your mix. Next. Okay, so now we'll go through each of these pieces. For translation, again, there's a lot of care, and you'll see that. So with translation, you could pick any translation model, translate all of your languages with it. What we wanted to do is we wanted to kind of see if there are better options for each language. So we select two translation models, Command A Translate and DeepSeek V3, both extremely strong translation models. And then we create a dev set and we translate it into all the languages using both of these models. Then you're going to use quality estimators like XCOMET XL or AfriCOMET to kind of see which model is the better translator for each language. So essentially what will happen is at the end of the stage, you'll have a list of languages and you'll have which of these two models is a better fit. Already, you're seeing that just with this one kind of optimization, you're improving the quality of your translation, right? And all of these gains kind of add up towards the end. Next. So now you have your translations. If they're of good quality, you can directly move them to the final mix. But if they're not, which again tends to happen, what you want to do is then you want to kind of improve, right? The first thing to do is improve prompts. And this is just general kind of information. If you could invest in better prompts or better generations, always try and improve your prompts because your generations will kind of be better also. Okay, for prompt level transformations, we follow steps from Mora et al., which is excellent work again from the lab, where we have prompt transformations that deal with naturalness, cultural adaptation, and difficulty enhancement. So with naturalness, we essentially remove any translation artifacts. With cultural adaptation, we recontextualize it with local information or relevant references. And with difficulty enhancement, we simply just increase the complexity of the prompt. And to explain this, here's an image from the paper. Next. So, for example, if you have the seed prompt, what is traditionally served with turkey on Thanksgiving, you translate it and you end up with a German translation, but you will have the word Thanksgiving. And this tends to happen in most translation models. So with naturalization, what you're going to do is you're kind of fixing all of these things, right? So Thanksgiving now becomes Dankfest. And now here you can again kind of add these complementary pieces, right? So you can culturally adapt it, where Dankfest becomes Weihnachten. I don't know if I'm butchering these words or not, but Thanksgiving then kind of becomes Christmas, which is maybe more culturally relevant to German culture. Or you could also do a difficulty transformation where you'll see that Thanksgiving is actually retained there, but instead of asking what is traditionally served, you're actually asking what's on the shopping list to to kind of serve these side dishes, right? So you're increasing the difficulty. One thing to understand here is not all of these things have to be done in a specific order. I mean, after naturalization is probably your best bet, but you can kind of pick and choose because some data sets might require two steps, some might require all three, right? So that is how you get better prompts. Next. After that, we have rich prompts. Now we want richer completions, right? This we do with another work from Kairi et al., which is, again, excellent work from the lab. So here what we do is when you're doing best of n, right, for better completions, you usually have a prompt and you get multiple generations from the same model, or you get multiple generations from a pool of models. Essentially, what everyone does is they pick the best completion via a reward model or some other technique. What this work does is it says, why are you selecting it? Why don't you just synthesize, right? Because all of these models have different strengths. Some are better at Yoruba in fact, some are better at Yoruba in translation. So what you want to do is you want to kind of play on these strengths. So what we do here is with Fusion, you have generations from Command A, Gemma 3, 27B, and DeepSeek V3. And you're going to get all of these three generations. And instead of then just picking one of them and throwing away all of that extra information, we use a fuser model, which then basically picks the best parts of all of these completions and fuses all these generations. Next. So just to drive the prompt, just to drive the idea home, you have a prompt, you have generations. With Fusion, what happens is you pick parts from all of these generations and you have a much richer completion at the end. And the paper actually shows that these lead to better win rates and much richer completions. Next. The final piece of this is machine translation data that comes from an excellent multilingual team. So more information is from the paper down below, Cosme et al. Essentially, what they do is they have a slightly different pipeline where they have parallel corpora and they do rule-based cleaning, they do fast text language ID, and then they also do some form of difficulty filtering with this model that actually picks examples that are difficult for translation systems. So it kind of gives you a better training data set. But one kind of fun thing here is they do quality estimation before that, because what this model does is it finds difficult to translate pieces of text. And if your text is broken, technically that's a difficult to translate piece of text. So what will happen is if you don't do the QE filtering, you'll get a lot of noise. So once you do that, you kind of take away the noise, and now you get like much richer kind of prompt completions to train on. And then they do back translation, only keeping completions that scored higher than the original reference. Another fun thing here is that in this data set, we actually use 98 languages, much bigger than the 70 pre-training. And this is intentional because we've seen that having access to a lot of these other languages also helps in cross-lingual alignment. So yeah, for more information, you can read this paper. And with that, I will now pass it to Alejandro. We'll talk about the clusters.
Yeah, thank you, Daniel. Yeah, so we have mentioned that we support 70 plus languages, but we didn't share which ones until now. So here's the full list of languages that we support. We cover 5 different regional clusters. So we have languages from Asia, Pacific, Africa, South Asia, Europe, and West Asia. And we have all languages from high resource languages like traditional Chinese and Spanish and English to some more low resource languages like Basque or Galician or Yoruba. So, oh, yeah, so the regional clusters, we have these 5 regional clusters. The European one has 31 languages, then West Asia 5, South Asia has 9 in 7 different scripts. So this is the cluster with the most different scripts. And Asia Pacific has 12 languages, Africa 10. And we group those 5 clusters in 5 regions into 4 training clusters. So we don't have a one mapping of region to cluster. Um, we did this for multiple reasons. One is that we basically experimented with different fine-tuning approaches, doing fine-tuning across regions and grouping models into different clusters. And we found out that by grouping different regions together, we got better performance because we could benefit from language transfer across the languages in the different clusters. So this is the data mix per cluster. And you can see that English is shared across all the different clusters. That's because English is the language with the most available data out there and usually the highest quality data. And it also help us and will help us later on to merge these clusters more effectively. And then the majority of the data in each of the clusters corresponds to the different regions that composes these clusters. We also include data from outside of these languages, a tiny bit of that, and code data, because as we mentioned, similar to pre-training, it helps with some reasoning tasks, and we also wanted the model to have a bit of coding capabilities, although that's not the main focus of these models. So now that we understand our synthetic data pipeline and the different regions and clusters, how did we actually do the post-training? We did our post-training in two different stages. The first one that was the supervised fine-tuning, and then we did some preference tuning. For the supervised fine-tuning, we tried to be quite efficient, and we did all the post-training in 16 GPUs for each of the clusters. It took less than 24 hours. We ran it through three epochs using cosine decay and cosine decay learning rate schedule, and you can see the values there. And we did run a few ablations to figure out what were the best hyperparameters per cluster and region. For the preference tuning, we did that on top of the supervised fine tuning, and it was extremely minimal. And we did that because we want the model to be easy to adapt to different tasks. So we basically just show the model its identity. So your name is Tiny Aya, and don't say your name is something else because you are Tiny Aya, and you support this list of languages. So very basic information for the model to be able to understand, its name and be able to provide the user the list of languages that it supports. And yeah, so the reason why we decided to just do this very lightweight preference tuning is because we wanted to prevent catastrophic forgetting. When you do preference tuning on models, you need to be very careful because sometimes, depending on how aggressive your preference tuning is, you can steer the model too much and it can forget some relevant information that it acquired during supervised fine tuning. But as I said, we also want to leave a lot of headroom for researchers and users to adapt and personalize and include more languages and new capabilities to the model. And we've heard from the community that if some people have difficulties with other models because they went through a very heavy post-training pipeline, and we want our model to be as adaptable as possible. Yeah. So finally, here's where everything comes together. We did one last thing once we have all the different clusters, all the different SFT models and the post-train models. We decided to do some model merging. And we did that for multiple reasons. One is that the region-specific SFTs are quite good at the regional languages, but because they've been trained on only a subset of those languages, the performance on out-of-cluster languages can be reduced, and not only performance, but also the safety and other capabilities of the model. So we basically, as we can see in this graph, once we have the different regional models and the model that has been trained on all the data, we merge those together using SimMerge, which is a merging method that it's quite effective, and it lets you choose the merge operator and order before actually merging. It requires a bit of unlabeled data to work, but it's quite fast to run, quite cheap, and yeah, it returns really good results. And we were able, as we will see in a bit, to recover a lot of the safety capabilities of the model and improve on key metrics. And yeah, if you want to learn more about all this merging strategy, check out the sim merge paper. It's also work done by the lab last year by one of the research scholars. Really interesting work. So post-training summary. Um, we have our synthetic data pipeline that consists of translation and then doing some prompt transformations like naturalization and complexity, etc. Then we have the fusion, where we use different models to generate responses, and we fuse them into one final response. We train 4 models from 5 different language clusters. We use SimMerge to combine different regional models and the global checkpoint to create the final models. And all of our models went through minimal preference tuning just for identity, safety, and preserving multilingual capabilities. And our models are quite good at translation, and that's because of our machine translation data that covers 98 languages. So it's more than the pre-training models, and it also helps us with cross-lingual transfer. And with that, over to Julia to talk about evaluation.
Hello, thanks so much. Yeah, let's see what is the outcome of all of that, all of these efforts. So I want to highlight a little bit more about also how we did it and why, not necessarily only about the numbers, because the numbers you can read by yourself and you can process them, but hopefully I'll help you understand a little bit how we interpret these numbers and what they tell us. And also that might inspire you for future investigations, because they also point out like the weaknesses of our model. So yeah, let's dive right into it. Thank you. So we kind of took, like it's an opportunity whenever you get to do something, some part of development, like with a fresh view. So what we wanted to see during development was really finding out how well our model is balanced across languages, not necessarily are we beating the competition, because that was never the goal of this project. We wanted to build a competitive multilingual tiny AYA, of course, but it was more important like whether it has this balance, and that's not necessarily something that is usually like top priority. And it's very important to realize that the choices made in development determine the final model. So we'll see this pan out later on. So I wanted to make a concrete comparison here. So usually what you would do to track during development, you would track the performance across languages. You would just take an average, you take some benchmarks, you get the average number, and then whatever decision you make is based on whatever pushes your number the most, the average. So that means you pick a few benchmarks, you get the average number, and then if you have a data ablation, for example, you would pick the one that scores higher. What we did instead, because we have 70 languages plus 70 plus languages, so only if we did an average, naturally high resource languages would weigh much higher than lower resource languages in there. So and then also we have more languages from Europe. That means in an average they would also dominate, but that's not what we want. So we want to know where do we fail on low resource languages, on regions that are, or especially scripts that are not Latin. So what we did for each of these clusters or regions, we picked a handful of diverse languages, diverse with respect to resourceness, script, and family, and those are the ones that we tracked in development. So only in the last week of before the release, we actually tested on all languages, and you can see that it transferred quite well. But this was also based on like having picked a diverse set, because otherwise you have bad surprises when you move to testing on a wider scale. And then for benchmarks, most multilingual benchmarks today are still multiple choice question answering questions or tasks, and these are very limited in terms of their expressiveness. While there might be very good knowledge kind of testers, they don't tell us anything about how well the model is able to generate like a complete sentence in that particular language. So we focus on generative tasks. These tend to be harder to get right. They're more realistic, even though we use translation to create them, but they're a better estimate, we feel, about like real user usage of the model later on. The evaluations might be a bit noisier because we often rely on LMM judges, but that was our call here. And for metrics, you could, like, it would be natural to just track accuracy, but what we did is we also looked at auxiliary metrics that we think are very important in multilingual modeling, which are language confusion. So how often does the model actually respond in the language of the prompt? How natural is the response? Again, this is a bit of a noisy estimate, but we can get some signal there. Instruction following, how much is the model actually able to follow the instruction that we give it? So this might or might not affect accuracy in some tasks, but this is some aspects that we want to highlight. And we want to track minimum performance, not only the mean, because we're very concerned about these like sharp drop off where we don't have balance because we lose performance on a few underrepresented and under focused language. Maybe let's call it like that. Okay. Next. Yeah, so in the paper we have a whole like a list of benchmarks that we looked at. I want to give you a quick overview here so that you see some of like the type of prompts that you might see in these benchmarks. So we have some open-ended ones like Dolly and Arena Heart, and there's a typical math, MGSM in different languages, typical translation templates, and then also some cultural knowledge testing. And for the discriminative task, these are the most common ones, I would say. So you have ABCD or whatever you want to choose from, or binary task even. And we also looked at safety, a few safety benchmarks. You can see that not all of these cover all of our languages. We prioritized on those that did, and we expanded some of them. So either through prompt translation, it's automatic and imperfect, but it's still better than not getting any signal. And we aggregated existing translations that were distributed and verified. So global MGSM had been translated by various researchers in various institutions in many languages, but they're not like aggregated in one place. So we did that for global MGSM to get a better view, because the original MGSM has 10 languages. And then if we aggregate all these translations that people have done and put a lot of effort to, we get to 35. Okay, next. And yeah, I mean, our lab, I don't know if you followed our releases, we often report win rates. This one we didn't. So that might be a question that is worth looking into. So the problem is, so win rate generally says, like, okay, I'm getting outputs from this model, I'm this, and then I'm computing with an LLM judge, how often would one output compared, one model be preferred towards the other based on their outputs for the same prompts, and then that's your win rate. The problem is there we have high variance as a metric. So if you maybe change a word, it changes the preference of the judge, and it flips the label, and then on average that kind of explodes. And then this is usually done on very small eval sets. So yeah, these averages get really noisy, and you don't really measure the real differences that matter. The problem is also for development, you want to have some kind of anchor in like how good is the overall quality of your model, not only like how good is it in comparison to the competition, because that's not necessarily your metric for success. And especially in the 70+ language space, each model has its own language distribution that might or might not be publicly available or known. So you would have to compare against 5 different models on win rates. So you have a lot of pairwise comparisons, and it gets very kind of messy to track. And yeah, interpretable, they're rarely interpretable. You can look into judge rationales and you get a bit of a signal, but yeah, there's a lot of known biases that come out at this kind of binary judging time. What we did instead is we looked at rubrics. So we defined rubrics for 4 criteria that we thought were all equally important, especially for this multilingual generative kind of focus that we had. So these are accuracy, instruction following, coherence, and fluency. And then we have a 7-point Likert scale for each of those. And for the final score, we average across those 4. So they have equal weight, and we mapped them linear to 0.1, between 0 and 1. And so the benefit is we get an absolute score for each of the categories for each language from an LLM judge. Again, they might not be perfect, but we anchor it on a scale, so it's to some extent interpretable, and we also make the judge reason about each of these rubrics before we get the score. So in that sense, yeah, we can verify and do spot checks. And because we do this averaging and we have absolute scale, we get more robust scores. Yeah, let's move on. I'm also aware of time. So some example here. So we had this problem, for example, you get a very easy win against Gemma in Welsh, but it doesn't help you at all because we get a 90% score. So are we done with Welsh? Probably not. So rather, if you look at these kind of absolute scale judgments, for example, for instruction following, you get, okay, directly assess the user question, good. You get a score of 7, and then for naturals, you still get the sig locator, some minor add natural phrases, so there's still room for improvement. You get a score of 5. For coherence, it's fine. Accuracy, again, there's some technical inaccuracies, so you know there is room improvement in terms of naturalness, and in accuracy, you wouldn't have that signet at all if you just went with the win rates. Okay, so let's look at some numbers. These are going to be a lot, but there's also even more in the paper. The purpose is that you can kind of estimate if you want to use a model for some of these tasks. Is TinyIA the right choice? Or if you want to build out some capacity in particular one of these tasks, then you can see this as like a kind of a guideline for where there's still a lot of room or not. So we have these discriminative benchmarks, and we find that Quen tends to lead on them. TinyIA is not too far off. So if you look at the absolute numbers, that's not too terrible. But yeah, I heard voices that were like, why is it not performing better at these? Because you're so multilingual, you're doing things so well. Why is that not happening? We did not really target those. So none of these were kind of really explicitly hill climbed on. We did not target them within the synthetic data generation that Daniel presented. Also, they measure knowledge recall in multiple choice formats. So it's measured by the log likelihood of the first character in the response, which is not at all representative of how would a natural, like, generative answer look like for this kind of question. So it does not provide any signal whether the model is able to generate text in a target language. So you can see this here as well. SmallMM, for example, covers only 6 European languages. Why does it perform so well on this task if it doesn't have this amazing performance across all the other languages in terms of generative tasks? So you can see here that there might be good cross-lingual understanding, but maybe not when you go to generative tasks. So let's move to the generative tasks. So this is really where TinyIA shines also, because we've prioritized this. So we have a table summarizing averages and standard deviation. Standard deviation here is very important because it captures this kind of drop in underrepresented languages. So it's kind of a red flag if there's a huge variance, because it means that some languages are clearly out of like support, or like where the performance is really poor. So on Dolly, we perform really, really well, really like far ahead across the competition. And then yeah, for Arena Hard, we can see that Quen is still leading. It tends to be much better, or like slightly better in the kind of coding task, but you see the variance is very high. So there might still be languages where we win, but it's not captured in the average. And then also the same for global MGSM. It's also a bit of a domain factor where math and code are more prioritized in other models, it seems. Our model is outstandingly good in Flores and WMT, which are translation tasks. So we'll look into those more closely. Yeah, what I said, like the standard deviation is like, if you look at these languages, you order these languages by resources according to their presence on the internet, you can see how there's like this steep drop for most competitors as well. We remain relatively stable. And yeah, translation, again, I will brush over these a little bit, very strong. Also compared to specialized translation models. We also prioritize multilingual safety in development. This is one of the metrics that we tracked during development, and you can tell because our model is quite stable across languages. It does not have these low resource jailbreaks at least not for the languages that we measured, because we made sure that we have safe performance across languages, and merging helped there specifically, where we merge with a globally trained model, and that kind of increased safety across languages. We also included cultural evaluations, and I think this is also a first, because most system reports don't go into detail there because we really wanted to know, okay, why, what's that is the understanding of cultural nuances looks like. Again, I would say let's go relatively quickly over that because we want to have time for questions as well. But we also experimented here with like adding chain of thoughts, and we compare prompting in the English language versus the target language. You can see that chain of thought gives us a huge boost in both cases, but overall the scores, the performance in English is higher than in the target language, which was still a little bit disappointing. And yeah, this is another benchmark just for cultural common sense, and same story, pretty competitive with other models around, but and specifically in particular regions like here, this was by country, so Nigeria, West Java, Greece, and Ethiopia. But yeah, all models perform better when prompted in English versus the local language. So it seems like multilingual models are still very English dominant, not only ours. So that is the case for all of the small models that we evaluated, because it seems that English has a richer and high quality turning signal at every stage, so models depend on it. And models' factual recall in English is also stronger. If you're interested in especially this cultural space, take a screenshot of this. There's a survey that we're running, and also be very happy to discuss if you want to collaborate or chat about this in general. So we're trying to find out where cultural awareness matters and where AI already reflects these cultural nuances and what kind of limitations we currently have. Okay, quick wrap up. Tanya Aya is leading on the long tail of languages, particularly African languages. Again, there are still some disparities with English, and with high resource languages, we're not fixing the problem of lower resource NLP, but particularly leading in translation tasks and competitive and open-ended tasks. Pretty good at generating target language contents and natural responses. Not as competitive in coding and technical tasks as average, but that's again it's a result of like what we focused on in our data kind of mix. And weaknesses that we noticed that are very shared with other models at this scale and multilingual scale are hallucinations, factual accuracy are still relatively problematic, I would say. And English prompting leads to high accuracy of responses, which is still, kind of still leaves a lot of room for improving multilinguality in LLMs.
All right, thank you, Julia. So yeah, I'm gonna go through this section fast so we have time for questions, but stay with me for a couple minutes. Let's look at on-device deployment and how Tanya works offline. So we also release quantized versions of our models at 3 different quantization levels, so 8-bit, 4-bit, and mixed precision quantization, which we recommend using the mixed precision because it reports the best results. We also studied how quantization degrades multilingual performance, and we saw that even for low resource languages where there is like orders of magnitude less information available out there and therefore less data to train our models, when we quantize the different versions of TinyAya, we do not lose as much performance as one could imagine. And we can see like around 2% drop versus the unquantized version of the model. TinyAya, the quantized version, can run in iPhone 17 Pro at 32 tokens per second, which is fairly fast, good for any sort of conversation. But even on older phones, previous to the LLM revolutions, like an iPhone 13, we can still run at 10 tokens per second. So should be good to have some sort of basic conversations offline on your phone. Yeah, so here we can see how TinyAya works for Hindi. There is another video using TinyAya in your web browser using Transformers.js. Pretty cool to see the model running without internet access and fully offline. All right, so conclusions. Let's wrap up, go for questions. We saw that balanced multilingual performance is at the same problem, and equity starts for these languages starts at the tokenizer and goes throughout the whole pipeline. We also saw that synthetic data and doing the transformations and the fusion is a really good way to obtain data in low resource languages. And merging is a cheap technique, so it doesn't require a lot of data. It's quite fast to run and it's quite powerful. And for evaluations, we saw that we don't need to just track the average. We also want to get the full picture and track the variance. So that was quite insightful and interesting to do in this project. We have still some open questions and what's next for this project. We've seen that quality still lags behind other models in some tasks like math and coding that are more reasoning heavy. Our model is a non-reasoning model, so I guess future versions of models could improve that. We support 70 languages, that it's quite good, but it's not everything. So expanding this while still maintaining the multilingual balance and performance is a challenge. As we saw, English prompting still outperforms other languages, and we are quite safe, but sometimes too safe. So there's a balance there that it could be slightly better. But yeah, as we mentioned many times, having multilingual performance at small scale is a design problem. And with TinyAya, we tried to solve this and design a model that is truly multilingual and can support as many languages and people as possible. And with that, shout out to the core team. Some of us are here today, but this project was possible thanks to many, many people. Also, many people across the company and many people in our community that helped us to review some stop words and other tasks. So it was really a true collaboration across multiple people. And with that, thank you so much for your time and any questions.